Hello everybody again. Today's lesson is going to be using definite integrals to find average values and area between curves, okay? So we want to get started with this. And when we take averages, we know that we sum the items and then we divide by the number of items, right? And if we're looking at some kind of curve that represents what's going on with a function, what we did in the past was we looked at discrete points along this function and we added these values, right? And then we would divide, well, we have 6 here, we would divide by 6 and we would get an average between here and here. But the problem is, look at all of these data points between these discrete points. We're not accounting for those, okay? So we have a way of doing that using a definite integral that works really, really well. So if this here is A and that is our B, then the average between A and B is going to be 1 over the difference between A and B, and then the integral from A to B of whatever our function is. Okay? So really nothing new from what we've been doing with definite integrals. It's just that we add this coefficient, if you will, out in front of the integral. It's still over the same area, if you will, of this x-axis. So if I wanted to take a function, and let's say I had a function f that was equal to, how about 3 radical x, and I needed the average of this function, however it looked, from, let's say, x equals 1 to x equals, how about 4, for example, okay? So I know that in doing this, I'm going to take 1 over 4 minus 1, right? Because isn't this my A and this my B? And then I'm going to integrate from 1 to 4 my function 3 radical x dx, okay? So the first thing I'm going to do is I'm going to simplify this and make it easier to work with. When I do that, I'm going to move this coefficient out in front. So I'm going to have 3, right? All over, as it turns out, 3 times the integral of 1 to 4. And then I'm going to convert this radical into x to the 1/2 dx, okay? Now, this one worked out really, really nice for me, that 3 over 3 just becomes 1, doesn't it? So I just have 1 as a result of this fraction and this particular coefficient. And then I'm going to integrate, right? So my integral, or the result of my integration, if this is n, is 1 plus n, right? Or n plus 1. So I'm going to get a 3/2 times x to the n plus 1, x to the 3/2 from 1 to 4, okay? Now, 1 times anything is itself, and 1 over a fraction is the reciprocal of that fraction, isn't it? So then I'm going to have 4 to the 3/2 minus 1 to the 3/2. All right? So I've got 2/3 times So 4 to the 3 halves, well, that's the square root of 4 is 2, and 2 cubed is 8. 1 to any kind of exponent is just 1. So this simplifies to 2/3 times 7, or 14/3. So the average of this function from 1 to 4 is going to be 14/3, okay? So anytime we want to find an average, all we need are our upper and lower bounds, and then we apply this fraction to it, okay? So that's how we can go through and get an average using a definite integral. Now, what happens when I want the area between two curves? Okay, area between two curves or functions, however you want to phrase that, okay? So when I'm looking at this, you know, maybe I have a function that looks like this, and maybe I have a function that looks like that. And I'm talking about, again, from A to B. And what I'm interested in then is this area in between these curves, okay? And so, you know, what we can do with this later on is say we have an original function that represents something we're doing. We make changes to the process, and now I get a result that looks like this. That area right there would actually represent the improvement from the original to the new state, okay? So what we have to do is we have to always know which is the upper and which is the lower function, okay? Because what this is the integral from A to B of the upper function, whatever that is, dx, and then we're going to subtract from it the lower function. And then I'll just say dx out here as well, okay? So let's do as an example two functions. One, f of x is equal to 3x squared plus 4. And the other function is f of x is equal to 2x minus 1. And we're going to go from x equals minus 1 to x is equal to 2. All right? Now, I have to know which one is greater, okay? Which one is upper and which one is lower. So I've got two options here. I can actually go in and graph these two functions and visually see which one is larger, or maybe I can pick a point here and see which one gives me a larger value, okay? So let's just pick 0 because it's in this domain, if you will, and it makes my math easy, you know, because if I put in x is 0, this first function becomes a 4. X is 0, this first function becomes a minus 1, okay? So I'm going to assume that this one is larger than this one, and we're going to talk about a variation of this later on. So, but for right now, this is larger than this, okay? Just go with me on that assumption. So I'm going to integrate from minus 1 to 2 the function f of x, my upper function, 3x squared plus 4, minus my lower function, and I guess I really shouldn't have used another f of x there, should I? Because I can't have two functions with the same name. So let's call this guy g of x, okay? So I'm going to subtract g of x from f of x here. Oops, wrong color. So I'm going to have 2x minus 1. And of course, that's all dx, okay? So I've got to now simplify my equation, all right? I don't want to work with all of this if I don't have to. So when I simplify that from minus 1 to 2, I'm going to have what? 3x squared minus 2x, 4 minus a minus 1, or 5, okay? And of course, we know that we just integrate each one of these separately, don't we? So when we do that, I'm going to get 3 over n plus 1, 3x cubed, okay, minus, the coefficient comes out in front, x is 1 over n plus 1, right? X to the n plus 1 plus 5 over x is 0. 0 plus 1 is 1. X to the 0 plus 1, right? And then that's all minus 1 to 2, okay? So this example is nice because it gave us nice, easy numbers to work with. So here, excuse me, I'm going to have upper limit 2 cubed minus 2 squared plus 5 times 2 minus my lower limit. I'm going to have minus 1 cubed minus a minus 1 squared plus a 5 times minus 1. Okay? So in here, I get what? 8 minus 4. So that's 4 plus 10. So I'm going to get 14 minus, so this is a minus 1. Minus 1 cubed is minus 1. Here I'm going to get a positive 1, but I'm subtracting it. So minus 1, which is minus 2. This is going to be a minus 5. So inside my bracket here, I should have a minus 7, right? Minus 1, minus a 1, minus a 7. So I'm going to have 14 plus 7 are 21, and then obviously it's square, and then whatever units we would have utilized in this particular problem, okay? So that's how I go about finding the area between two curves. I have to make sure I know which one is upper, and then I have to subtract the lower function from the upper to do my integration, okay? Now, that's for an example where one is for sure going to be above the other one. But sometimes we have a situation where the graphs actually cross, okay? And we have to be able to account for that. So let's look at an example here. F of x is equal to 12 minus 3x squared, and we'll call g of x 4x plus 5, okay? So just as a way of estimating so that you can kind of see the picture, this particular problem here is going to intersect y at 5, okay? And this problem is going to do something just about like this, okay? Now, in order to find the area between these two curves from, and we're going to go from 0 to 3, okay? So I'm looking for, and we'll say 3 is out here someplace. All right. I'm looking for this area. Okay. So I've got to be able to do something to find an area here and the area here. Well, in this part right here, up until where they intersect, f of x is my upper function, isn't it? Once I pass the point of intersection, g of x becomes the upper function, okay? So here I'm going to integrate f of x minus g of x, and then here I'm going to integrate g of x minus f of x. But the key to all of that is what? It's this point right here, okay? I have to know what that point is, and so whatever that is, I'm going to integrate from the origin, since I'm talking about 0, to this point for f of x minus g of x. And then I'm going to start, this will be my lower bound when I integrate g of x minus f of x up to here, okay? So how do I find where these two functions integrate? Well, they're going to have the same value there, right? So if they're going to have the same x and the same y, that means they have to be equal to each other at that point, doesn't it? So let's set these two functions equal to each other. Okay, and that's a 4. If I set them equal to each other, I should be able to find these coordinates for this intersection. So let's go ahead and we'll move this side over here and get rid of the negative on my x squared term. The 4x will stay the same. I'll be subtracting 12 from both sides. And so that'll give me a -7, won't it? So what do I do now? How do I solve for x? Well, this is a good old factoring problem, isn't it? So I start thinking through this. Well, I have to have the first terms of my FOIL to equal 3. The only factors of 3 I have are 3x and x, right? Now, I've only got 1 and 7. So how do I use 1 and 7 here? And because my signs are going to be opposites, aren't they? So I can put a 1 here and a 7 here, but then I'm going to get a 21, right, when I FOIL it, and that's not going to get me to the 4. So if I put the 7 here and the 1, my outer is a 3, my inner is a 7, and I know there's a relationship between 7 and 3 to give me a 4. So let's put 7 and 1 here. So this is positive, right? And we always put our second sign here with the largest factor. And now let's look at it. So I get 3x squared minus 3 plus 7. That's going to give me my 4 minus a 7, right? So let's look at what we've got here. Zero product principle tells me I look at 3x plus 7 equals 0 and x minus 1 equals 0. when I go through the process of this, I'm going to end up with x is minus 7/3, and x is equal to 1. Now, I was looking for 1, but I got 2, and that's okay. This is where these two things intersect. So obviously this curve comes back around and intersects over here. It doesn't matter to us. We're looking for the area from 0 to 3. So I only need that intersection x value, right? So I know that x is going to be 1 there. So I can integrate from 0 to 1 and then 1 to 3. Okay? So let's do that. So I'm going to integrate from 0 to 1, my f of x, 12 minus 3x squared, minus my g of x, which is 4x plus 5, right? And then I'm going to add to that, because this is that area, the area from here, which is going to be the integral from 1 to 3 of g of x, 4x plus 5, minus f of x, 12 minus 3x squared dx. Okay? So I just have two different integrations that I have to do. So let's simplify from 0 to 1. I'm going to have minus 3x squared. I'm going to have a minus 4x. And I'm going to have a 12 minus a 5 or a 7 here, aren't I? And then over here, from 1 to 3, I'm going to have what? A positive 3x squared. I'm going to have a positive 4x. And then I'm going to have a minus 7 here. Okay, just an old habit for me. I go through these and I make sure I'm in descending order. Okay, all right, so let's integrate this guy. N is going to be 2, so I'm going to have minus 3 over my n plus 1, x cubed, minus 4, n is 1, right? So n plus 1 is 2, x squared, plus, and I know the integral of a constant here is going to give me 7x, and that's from 0 to 1. I come over here, I'm going to go through the same process. N is 2, so I'm going to have 3 over 3 x cubed plus 4, n is 1 over 2 squared minus 7x, and that's, of course, all from 1 to 3. So it may help you to just go ahead and bracket all of this so you see what you've got going on, okay? So now I'm just going to substitute my upper. This just is minus 1, so I'm going to have minus 1 times 1 cubed minus, this is a 2, 2 times 1 squared plus 7 times 1, right? That's the upper minus the lower. So I'm going to have 1 times 0 cubed minus 2 times 0 squared, plus 7 times 0. All right? Now, I'm going to add to that the result of this integration, all right? So I'm going to add 1 times 3 cubed plus 2 times 3 squared minus 7 times 3. And I'm going to subtract from it the lower, which is going to be 1 times 1 cubed plus 2 times 1 squared minus 7 times 1, okay? So what do we have here? In this first one, I get minus 1, minus 2, so that's minus 3. Minus 3 plus 7 is going to be 4. That's all going to be 0, isn't it? So minus 0 plus 27, which is 3 cubed, plus 3 squared is 9, times 2 is 18. So 27 plus 18 is going to give me 45, minus 21 should give me a 24. Okay, 45 minus 21. And then over here, I'm going to have what? 1, that's a 1, plus 2 is 3. 3 minus 7 is minus 4, but because it's subtracted, it's going to be plus 4, isn't it? So here I'm going to have 4 and 24 and 4, so 24 and 8 is 32. All right, and again, some sort of square units for finding the area between two functions that actually intersect with one another, okay? So it's important that you understand that how I can find their intersection, how I can, for example, remember over here, I plugged in a 0 to figure out which one was the upper function, all right? See, in this one, I was able to use my graph to determine that g of x was upper. But I may get a problem where I don't have a picture. And so I'm going to have to plug in points in between these intersections and these bounds to determine which function is upper and which is lower, okay? So to summarize what we did today, we used definite integrals to find average values, where we just simply use the difference of the upper and lower bounds, and then do our normal integration, because remember, this is getting all of these values that are in between these discrete points, okay? And then we also did integration to find the area between two curves. And so the upper minus the lower, that's the key here in order to make this work. So when we have an intersection between the two, we can set them equal to 0, find those intersection points, and then use this intersection point as the upper for the first part, and then the lower for the second part. And then we just have to make sure we know which is upper and which is lower, okay? So that concludes this lesson on area between curves using definite integrals, and I will see you guys next time.